In this module, I'm going to go over a few additional comments about RSA and some intricacies of it. RSA relied on the fact that you were going to find primes and then do something with it to find the public key and the private key. So the question is, how do you go about finding them? Well, clearly, you can't just choose a random number and try to see if it is a prime by factorizing it, because the whole observation was that factoring is difficult, and that's what made RSA secure, because somebody who had access to the factorization, namely the person who chose the two primes P and Q, could factorize it very easily, but somebody who just knew the product couldn't factorize it very easily. So that means that we need to have some way to find primes without having to factor a randomly chosen number. Now, Fermat's little theorem comes to help, but not fully. So let's first review what Fermat's little theorem is. So it says if P is prime, then a to the power P minus 1 is 1 mod P. Let's look at the inverse of this. Inverse of this would be P is not a prime implies a to the power P minus 1 is not 1 mod P. Well, the problem is the inverse is not true. So let's focus on the inverse of Fermat's little theorem. Even though it is not true, what if it is probabilistically true? Well, now this violates all the things we have been saying about proofs in this class, which is that when I prove something, I want to be true with certainty. And I, in fact, made a big deal about the fact that always is not the same thing as almost always. That said, I want to sort of go on this line of thinking because that actually turns out to be useful in this context. What if it is probabilistically true? That is, for half the numbers, it is true. For the other half, it may not be true, but for at least half the numbers, the statement is true. That is, if I choose A randomly, then if P happens to be composite, then a to the power P minus 1 is actually not 1 mod P. Then what we could do is we could try for a value of A, compute a to the power P minus 1 mod P. If this equals 1, then we are going to say that P is a prime with probability half. If it's not equal to 1, if a to the power P minus 1 is not equal to 1, then clearly P is not a prime, and this follows from contrapositive of Fermat's little theorem. Note that if the theorem is true, its contrapositive is also true, and that means that if a to the power P minus 1 is not 1 mod P, then clearly P is not a prime. Let's continue from the previous slide. Let's try this for multiple values of A. So let's imagine that we try it for S values of A, randomly chosen different values. If I see that for the first value of a to the power P minus 1 mod P is still 1, that means P is a prime with at least probability half. If for two numbers the same thing works, then the probability that I will get it wrong becomes 1/4. For three numbers, it becomes 1/8, and so on and so forth. So the more numbers I try, and a to the power P minus 1 mod P is still 1, I get better and better confidence that P is actually a prime. So if I try this for S different values, the probability that P is a prime is going to be 1 minus half to the power S. Clearly, if any one of them is not equal to 1, then P is not a prime, in which case we should just discard it, because if a to the power P minus 1 mod P is not 1, then I know for sure that P is not a prime. So we said, okay, let's try to find if P is a prime by inverse of Fermat's little theorem. Even though the inverse is not quite true, we'll ask the question, what if it is probabilistically true? Well, it turns out that we are not so lucky. That is, the statement is true for most numbers, but not all. There are these numbers called Carmichael numbers, and I have a link over here that you can Google more on. These are numbers that behave just like primes as far as Fermat's little theorem is concerned. In other words, they are composite numbers, but if you evaluate a to the power p minus 1 mod p, then the answer turns out to be 1. Luckily, there aren't very many of them, and that means that we can circumvent them by using some more tricks, but those tricks are outside the scope of this class. So I'm going to ignore Carmichael's number, and I'm going to sort of start with the claim that I'm going to check multiple values of a. If for all those values a to the power p minus 1 mod p is 1, then I will have a great confidence that the number that I've chosen is a prime. Note that if I try for say 100 different numbers, then the probability that I have an error is going to be something like this, which 2 to the power minus 100. That means the number that I've chosen is not a prime, but I believe it is a prime, happens with such a low probability that it would be okay for practical systems. There is another problem. The other problem is, if I choose a number and it happens to be not a prime, then I'm going to discard it. I am going to choose a different number. So now the question is, how many numbers would I discard before I find the number that I will consider to be a prime? This is where there is an important result. Again, the proof of this is outside the scope of this class, but it says pi of n is roughly n divided by ln of n. ln is a natural log. Pi n is the number of primes that are less than or equal to n. Now I'm going to make a few changes to this that are mathematically not valid, but I'm going to do that because it will simplify my proof, and if you are ready to do a little bit more work, you can complete the proof without these assumptions. It's just that the explanation becomes a little bit more difficult to follow. So I'm going to make a few little changes to this. First, instead of log with to the base e, I'm going to change it to log to the base 2. Observe that log n to the base 2 is the length of n in binary. Note that this is not such a big difference because I'm basically changing a constant factor, because if I do something like log n to the base 2 divided by log n to the base e, then this is basically log e to the base 2, which is a constant. So I'm not changing this definition of pi of n by large, I'm changing it just by a fraction. And that's why if I were to do the proof exactly right, then it's going to get into this factor all the time, and I don't want to get that factor right now. I want to make this simple. Another thing I'm going to do is I'm going to assume that most of the primes that are here, in fact all of the primes that are here, have the same length as n. Now this is clearly not true, but again what this changes is a constant factor, so I'm going to ignore that for now. So what do I mean by same length? I mean that numbers less than n that are primes also include these one-digit numbers. I'm going to sort of assume that ignoring those, I have primes that are roughly equal to this. With the changes that we observed, with the changes that I made, I'm going to think of pi of n is roughly n divided by log n to the base 2. Again, as I said, the statement is not exactly true. There is a constant factor that is missing, but I want to ignore that constant factor for now. So that means if I choose a random number with log of n to the base 2 digits, which is basically the same length as the number that I'm looking for, how long a number I'm looking for to be a prime, then the probability that it is prime is 1 divided by log n to the base 2. Because I have roughly every log n numbers I have a prime, so if I'm choosing a number randomly, then the probability that I get a prime is 1 divided by log n to the base 2. So that means we can take this further. Again, if you take a statistics course, you will learn new terminology that will make these statements precise. But essentially, I will need to choose log n to the base 2 numbers to find one that is actually a prime, or that is one that we believe to be prime. There could be a small error in terms of our belief, but that error is so small that we're going to ignore it. So if I choose 1,000 numbers, each with 1,000 bits, then we are expected to find a prime. Not that this is a lot of work, but it's feasible. I can choose 1,000 numbers. I can run it for each one of them, say 100 values of A. It will be a lot of work, but I can do that in a reasonable amount of time. Note that the prime number that I will get by this, however, is going to be in the range of 2 to the power 1,000. Note that the constants that I've talked about, we are slightly off, but I have chosen to drop those constants for simplicity. For those of you who are interested in getting to know more about it, I'll be glad to talk about it elsewhere. And the exact math is also available in other places as well. But the reason I wanted to go over this in this simplified form is because it shows that one of the parts of RSA that we skipped over, which is how do I find primes, can actually be done reasonably easily. Furthermore, remember that finding the values of P and Q is something you do once. That is at the beginning to decide what your private and public keys are. You don't change those primes during encryption and decryption, so that means the cost, even if it took, say 10 seconds, it's not a big problem because it's the time required to create new keys. It's not the time required to send messages. Now the time taken is a lot less than 10 seconds, but that was to illustrate that this is something that cost is not a big factor as long as the cost is, a few milliseconds, few seconds, even a few minutes would be okay, because it's something that is not to be done very frequently.